Hello everyone, in this session I will share with you how to do the inverse Z transform. Inverse Z transform can be performed using three methods, that is the long division method, partial fraction expansion method, and the residue method. For long division method, the Z transform of the signal, which is expressed as a ratio of two polynomials in Z, is simply divided out to produce a power series in the form of an equation. It's like this. Okay, so xz is the numerator divided by the denominator, or equal to the summation of the an z inverse. Okay, so when n equal to 0, so all the n will be substituted with the 0. When n equal to 1, all the n will be substituted with the 1. Okay, so this is the summation of the equation a n z power of minus n. And an is the coefficient of the value of xn. So if the xz can be expanded in a power series like this, the coefficient represents the inverse sequence value. Now let's look at the example. A system has an impulse response of the hash n equal to 1, 2, 3, and output response of yn equal to 1, 1, 2, minus 1, 3. Determine the input sequence xn by using the long division method. How to solve this question? We actually can solve by using this one. Hash n change to the z transform hash z, and yn change to z transform, so we have the yz. So as you know, the output is equal to the input multiplied with the system. So we need to find the hash. This is the impulse response system, hash n. So yn is yz, because all is transformed to the yz. So yz is equal to hash z multiplied with the xz, but we don't have the x, okay, input. So what we can do is xz equal to yz divided by the hash z. So this can be illustrated here. So we transform all the input hash n, transform to the z transform hash z. Okay, I believe that all of you know to transform the sequence, numerical sequence, into the z transform. Okay, and the yn to the yz, so we have this one. So yz is equal to the hash z multiplied with the xz. Okay, since we only have the yz and the hash z, we don't have the, and we need to find the hash xz, so yz divided by the hash z. So this is the yz and the hash z. Okay, so we need to find the xz. So xz is equal to yz divided by the hash z. Here we can have a long division method. Okay, so yz is in the inner part. We put it inside. And hash z is outside. Okay, now we can do the long division. Okay, we need the 1 here. Okay, we need the 1 here to have the 1, so we can put 1. So we have 1 plus 2z inverse plus 3z power of negative 2. So we minus, when minus 1 minus 1, we left nothing, 0. So 1z minus 2, you get minus 1z. 2 minus 3, you get minus 1. Okay, so then we'll bring down this value, so you have minus z minus 3. So how to get minus z power of minus 1? How to get minus z minus 1? So we can use a minus z minus 1. So when we multiply with 1 here, so we get minus z power minus 1. Okay, and 2 multiply with the z inverse here, so we get minus 2 minus power of minus 2, and then this one also have a 3z minus 3. So we minus, so negative z inverse minus minus z inverse, so we'll cancel out. So minus 1 here plus with 2, so we have positive. And then this one negative plus with 3, so you have positive 2. And then we bring down this one, you get plus 3z power minus 4. Then how to get z power minus 2? So we can plus 2 z power of minus 2 plus 1 only. So you have this one is z power of minus 2. And then this one is plus with 2z minus 3. And then we have plus 3z minus 4. And then we minus. So what is the answer? So we left nothing. So we left 0. So we left 0. So the answer is your xz is 1. Okay, is this answer? 1 minus z inverse plus z power of negative 2. So the inverse z transform of the xn is equal to 1 minus 1, 1. Okay, this transform from here. If you be free, you can do the exercise 5.12, calculate the inverse Z transform using the long division method. Another method is the partial fraction expansion method. This partial expansion method is used to decompose the signal or the system transfer function into some of the standard function. So the denominator of the transfer function need to be factorized into prime factor. Now let's look at the example. By using the partial fraction expansion method, find the inverse Z transform of this. Okay, so we need to factorize the denominator here. So I factorize like this. So 1 here, I can have a 1, 1. For the 8 here, so I can have 4 and 2 to become 8. 4 inverse and 2 inverse. So that I can have the 6 when I plus it. So I total out, I can get the 8. When total out, I can get the 6 inverse. So this one is equivalent to A over 1 plus 4 inverse plus B 1 plus 2 inverse. So I take this whole part to the right hand side. So I left minus 4 plus 8 inverse equal to A 1 plus 2 Z inverse plus B 1 plus 4 Z inverse. So now I want to assume the Z inverse value. So if I assume the Z inverse is equal to negative half, okay, so I substitute the Z inverse to negative 0.5. So negative 4 plus 8, negative half equal to B. So this one, when I substitute the Z inverse equal to negative 0.5, I will get 0 here. And I left B 1 plus 4 multiplied with negative half. So this one is negative 8 equal to B 1 minus 2. So this is equivalent to, I bring this to the left, so I have a B equal to negative 8 divided by negative 1. So I obtain 8. Next, if I assume the Z inverse to negative 1 over 4, so this value is depends on here, okay. So now I substitute the Z inverse to negative 0.25 into the equation. So this is negative 4, then negative 2, 1, A 1 minus half. So A is equal to negative 6 divided by negative positive 0.5. So this is equivalent to negative 12. So the hash z value is, you substitute the a is equal to 12 into the equation, and plus with b, the answer is b is 8. So 8 divided by 1 plus 2 z inverse. So I obtain the hash z. Now I want to obtain the hash n, so I inverse the z transform. So I obtain the hash n equal to negative 12. Okay, so negative 4 power of n plus 8, negative 2 power of n un. Okay, do you know how to obtain this one and this one? As you know, the z transform of the un is 1 over 1 minus z inverse, or z over z minus 1. So if I use this equation, so for the scaling, okay, now I'm talking about the scaling. For the scaling, I have the ANXN equal to X A inverse Z. Okay, so this is the formula for the properties for the scaling. If I have the ANXN, I will have the X A inverse Z. Now if you have this one, so you can find the xn. Okay, if you look at here, that is the A inverse Z. Okay, A inverse Z. And for the un, the Z transform of the un, you can use 1 over 1 minus Z inverse. Okay, and for the scaling one, is you substitute the Z inverse to a z inverse. And then for this one, z over z minus 1, you need to substitute the z with z a inverse. Okay, this one. And now you compare your this value with the answer that you obtain. Okay, you obtain 1 plus 4z inverse. So basically, it's more or less you use this value, okay? So this means when you use this value, the z inverse is substitute with a z inverse. Okay, a z inverse. So if you compare these two, this means that the a here is 4. Okay, the a here is 4. That's why. Okay, so this one is a 1 minus, right? 1 minus. So that should be, this is 1 plus. So this one you have the minus 4. Okay, the a is minus 4. Therefore, when for the scaling factor, for the scaling, so you have a power of n, so it's a minus 4 power of n. Similarly to this one, if you compare with this one, this means that the a here is minus 2, right? It's a minus 2. So therefore, if you follow this one, it's a minus 2 xn. But your xn is referred to the un. Okay? So I hope you can understand how to find the inverse Z transform using this one. Using this partial fraction expansion. Especially for the last part, when you want to transform from the Z transform to the xn. If you be free, you also can determine this. You also can do this exercise by determining the inverse Z transform of this question using partial fraction expansion method. Next is the residual method, the third one. To find the inverse Z transform is the residual method. So the xn is for the summation of residue for xz z power of n minus 1, where the residue for the pole of order m at z equal to alpha is this formula. Okay, is this formula. Now let's look for the example. Okay, if you look at this question, the highest order of z, okay, is 1. Okay, the highest order of z is 1. So this question, the xz has two poles of the order m equal to 1. At z equal to 1 and z equal to 2. So the m is referred to the highest order of z is 1. So m is 1. So this m can be substituted into this formula. Okay. So now I want to find for the poles at z equal to 1. Okay, for pole at z equal to 1, then the residue is, okay, we follow this formula. Okay, we follow this formula. 1 over m minus 1. 1 over m is 1, so 1 minus 1 you get 0 factorial. Limits alpha, or we should say z goes to 1, then so differentiate 0 and dz0. That is because the m minus 1 and m minus 1 is 1 minus 1, you get 0. So z minus alpha is referred to the pole at z equal to 1. So you substitute with 1, alpha equal to 1. Okay, this xz is the xz value here. Okay, so I write down here z minus 1, and then this is the xz value, and then this is the multiplied with z power n minus 1. So now limits. Okay, so this z it becomes n minus 1 divided by n minus 2, because this one can cancel out. So we substitute the z equal to 1, so we have z power of n divided by z minus 2. So this is equivalent to 1 power of n, 1 minus 2. This is 1 power of n minus 1. So it's minus 1 power of n. And then for poles at z equal to 2. So residue equal to 1, 0 divided by 0 factorial. Limits z goes to 2. Differentiate d over dz0. Z minus 2. And then the xz times with z power of n minus 1. So this is z times with z n minus 1 divided by z minus 1. So this equivalent to z times z power of n divided by z minus 1. So this one can cancel out. So I substitute the value equal to 2, z equal to 2, so I have 2 times n minus 1. So I have 2 power of n. So the xn is equal to minus 1 plus with 2 power of n un. Okay, so that's all for the residual method.